Today, we want to talk about exponents. We're going to continue our exploration of our operations so we can understand them moving forward. And today we're going to look at exponents. Every time so far, we've had two things. When we talked about addition, we had two things. We talked about multiplication, two things. We talked about multiplication and addition together. There was two things. So with exponents, we're going to have three things. One of them is going to be what the exponents represent, and we already talked about that on Wednesday. Exponents represent repeated multiplication. So if I have a bunch of things that are all the same and I'm multiplying them together, I can say, let's summarize this with an exponent. So 2 times 2 times 2. 2 is the base. That's what I want 3 copies of. I can't put the 3 in front of the 2 because that's for addition. So I put the 3 on the other side. So I had to put it somewhere, put it on the other side. But I didn't want it to look like 23 or 2 times 3, so I make it a superscript. That's what we did back in the day. Like I was there. So we can either write 2 to the third as 2 with a 3 superscript, or single line syntax when we're texting our friends cool math things, we would say 2, and then we would write the to the symbol followed by the 3. And then we would pronounce both of these symbols the same. We would say 2 to the third. If we want to sound fancier, we would say 2 to the third power. We could also say the third power of 2. But when we say it that way, it does a weird thing to our voice, as you just heard. So exponents represent repeated multiplication. This brings us to some interesting interactions with exponents. So if I have, let's say, an expression, if I want to take an expression with exponents and I multiply it by another expression with exponents, if we think about what these exponents represent, the rules aren't so arcane. So we might remember what happens when we multiply x squared times x to the third. Does anybody just remember this rule? You might have been programmed this when you were a kid, around 13 or 14. What's x squared times x to the third? What do we get? Anybody remember? It's okay if you don't.
X to the fifth?
X to the fifth. We add the exponents. But there's a reason that it makes sense that we add the exponents. X squared means x times another x. X cubed means x times x times x. There's what x cubed means. X, and x times x is what x squared means. So it makes sense that if we want to multiply x squared times x to the third, we just count all the things that we're multiplying. Count all the times we're multiplying x. That's why we get away with adding the exponents. Not because it's some weird rule, that's just how numbers behave. Any questions? So we could think of this as a rule for exponents, but that's just how numbers behave. That's why it's a rule in the first place. This is a super pornographic example. I have to switch to a different variable. So we want to think of exponents as being multiplication. So if I have, say, x to the fifth, and I want to divide this by, say, x squared, in this case, we could just think about what x to the fifth means and what x squared means. And that's why we're going to subtract the exponents. So the x to the fifth has an x times an x. It's 5 x's, so I'm going to write x, and then x, x. And the x squared just means an x times x. So the reason that we subtract the exponents is that we have 5 x's being divided by 2 x's. 2 of those x's are going to cancel out of the numerator and the denominator. Something divided by itself is equal to 1. So that's why we can subtract the exponents. When multiplying things with the same base, we add the exponents. We could write that down as a rule, but I would rather we just recognize that as what we would naturally do because that's what exponents represent. When we divide things with the same base, we subtract the exponents because that's what exponents represent. If I raise an expression with an exponent to another exponent, say x squared to the third, I have two sets of exponents. First of all, what is x squared all to the third power? What's this equal to? What do we do? It's okay if you don't remember.
Multiply.
We multiply. So we get x to the 2 times 3 is 6? 6. So, but that, of course we do that because that's what's going on here. The x squared to the third means I have 3 copies of x squared. It's x squared times x squared times x squared. And each x squared is 2 x's. So I have an x squared. So that's an x times x. Then I have another x times x for the one in the middle. And then I have yet another x times x for the one at the end. So what we're doing when we say x squared to the third is that we're multiplying 6 x's together. And so it makes sense that we would write that as x to the 6th. So the way these operations are going together, the reason that we add the exponents is because the exponents represent repeated multiplication. I've got 2 of them here, 3 of them here. We're all multiplying them, 5 total. I've got 3 copies of 2 x's. That's going to be 6 x's in total. If I divide an x by an x, I get 1, and so I can cancel it or simplify that part of the fraction. One more thing to go along with this. When we learn things in math, we have to learn them backwards and forwards and upside down. If I take this x to the 5th over x squared and flip it over to an x squared over x to the 5th, now I've got the 5 x's in the denominator. So I've got an x times an x. Those are the ones that are going to cancel out with the x squared in the numerator. But I still have 3 x's left over in the denominator. So when the x's cancel out of the numerator, I have x divided by x. That leaves behind a 1. And then I have 3 x's in the denominator. So when I have x squared over x to the 5th, I end up with 1 over x to the 3rd. Earlier, we said x to the 5th divided by x squared. We know the rule is to just subtract. 5 minus 2 is 3. There are 3 x's left over. When we have x squared over x to the 5th, we kind of did the same thing. 5 minus 2 is 3, but the bigger number was in the denominator. We could also subtract 2 minus 5. If I look at x squared over x to the 5th and I just subtract 2 minus 5, 2 minus 5 is negative 3. So I can read 1 over x to the 3rd as x to the negative 3. So negative exponents are a thing. Negative exponents just indicate the base is in the denominator or the opposite side. So I did top minus bottom, 3 on top. Top minus bottom, negative 3 on top. Bottom minus top, 3 on the bottom. If I did the bottom minus top, 2 minus 5, I'd have x to the negative 3 in the denominator. We wouldn't write that, but it's certainly the same. It certainly means the same thing.
So we wouldn't use a negative exponent to represent the answer to that question.
No, we wouldn't use this as an answer. We wouldn't say as an answer 1 over x to the negative 3. we would either write it as, we would simplify this as x to the third. If the base, when we really want to write x to the something, so x to the negative 3 is fine, but 1 over x to the negative 3, that looks weird. So I'm not going to put a box around that. No box for you. Any questions? But we want to be aware that these are things that we can do. These are moves that we have. Any questions? These rules are not some weird arcane things that we decided would happen. These are things that we discovered happen when we define exponents. We, like I was there. So that's just number 1 on exponents. Exponents represent repeated multiplication. Because of that, it gives rise to these properties of exponents. So we could think of the properties of exponents. Any questions? That's number 1 under exponents, and I said there were 3. So let's go to number 2. See page 2. Took me a whole page to be like exponents are repeated multiplication, typical. All right, number 2. That's just like me to talk too much. Number 2. This is the one that I forgot to insert yesterday before I asked the distribute question, but exponents are repeated multiplication, and that means exponents go before multiplication. Exponents before multiplication. Just like multiplication is repeated addition and multiplication before addition, unless parentheses. Same rule applies for exponents. Exponents before multiplication unless parentheses. As usual. So if you have to make the decision to do multiplication and exponents, or if you have to simplify, to simplify your expression, you have multiplication and exponents, the exponents go first. Do the repeated stuff first. So for example, if I have an expression that says 5 times 3 to the second power, I'm not multiplying 5 by 3. I'm multiplying 5 by 2 3s. So the exponents go first. If we think about what 3 squared means, 3 squared means 3 times 3. So this is not 5 times 3. It's 5 times 3 times another 3. So the exponents go first. So this is 5 times 9. And then 9 times 5 is 45. Because 3 squared means, this whole expression means 5 times 3 times 3. The 2 only applies to the 3. If my expression came out 45, I'm like, oh, hang on. I wanted the 5 to be squared first. I wanted this multiplication to go first. Then we'll have to use parentheses. So, unless parentheses. If I have an expression that says, if I want the 5 times 3 to go first, I would have to write it this way. Now the parentheses say, do the 5 times 3 and square the result. So now I have a different expression. 5 times 3 is 15. And then we'll square the 15, and that's 225. So 2 different expressions. Because what we're dealing with on this side, what's being squared is the product of 5 and 3. So I'm taking a 5 times 3 and another copy of 5 times 3. That's what I'm multiplying here. 2 5s and 2 3s. Where in the previous one, it was 1 5 and 2 3s. So number 2 of exponents. Exponents before multiplication unless parentheses. Any questions? All right. If you're looking at all the stuff that we're doing and think, Leach, aren't we just doing PEMDAS, but like taking too long to do it? Yeah, we're doing PEMDAS and we're taking too long to do it because PEMDAS is trash. You're not a robot. I don't want to try to program you with an algorithm unless it's absolutely necessary. I want to teach you how to read, but I want to teach you how to read math, which is a very difficult written language. It totally makes sense, but mathematicians, we wrote a weird one. All right. So exponents before multiplication unless parentheses. That's number 2. And that fits, that's parallel with multiplication is repeated addition, multiplication before addition unless parentheses. Now the next one is exponents distributing. Exponents distribute over some operation. So think about the parallels we've had with multiplication and addition, and how I just drew some parallels between exponents and multiplication. What must exponents distribute over? What operation will exponents distribute over?
Addition?
Not quite. Multiplication distributes over addition, and multiplication is repeated addition. Exponents is repeated multiplication, so what should exponents distribute over? And there's a hint to it right up here in this example, which is going to be the example over here. Exponents distribute over multiplication. So what I mean is we can see an example of an exponent that can be distributed over some multiplication up in this example where I said the square of the product of 5 and 3. That just meant the product of 5 and 3 and another 5 and 3. And what we have is 2 5s and 2 3s. So I can read 5 times 3 all squared as 2 copies of 5 times 3 or 2 5s and 2 3s. If we want to use the distributive property, 5 times 3 squared. If I distribute the 2 over the product, over the multiplication, I can say that's 2 5s and 2 3s. 5 squared is 25. 3 squared is 9. 25 times 9 is still 225. Exponents distribute over multiplication. And division, because if it's good for multiplication, it's got to be good for division, except by 0. So if we just think about the organization here, this is 2 5s and 2 3s. It just means 2 5s and 2 3s. And I can rearrange these because it's multiplication. If I just switch the 5 and the 3 here, and then it's associative, so I can group these up this way. And this is not some weird arcane rule that we made up to make high school and college students suffer. This is just how numbers work, and we're making observations about how numbers behave. Any questions? All right. So those are the rules for exponent. There were 3 of them this time. And we're just going to practice using them in a bunch of different expressions. How's everybody okay? Notice that exponents distribute over multiplication, but they're too far away to distribute over addition. Exponents do not distribute over addition. Exponents do not distribute over addition. I'm going to write that down, and it's very dangerous, and I always question whether I should do this or not, but I'm going to do it anyway. Exponents do not distribute over addition. I'm going to put an exclamation point up here too. I like that custom in the languages that have the upside down exclamation point, because they're like all telling you at the beginning of the sentence, hey, you should start shouting. With a question mark, it's not as important. If you put a question mark at the end of a sentence, you only need to know that right at the end. If this is a question mark, you don't need to know you're asking a question until the very end, because then you just make it go up at the end. Exponents do not distribute over, oh, it's a question, addition. You just like up at the end. But if I get all the way to here and then find out I should have been shouting, I might go, you should have told me that at the beginning. So it's like, oh, hey, start shouting. I might go, exponents do not distribute over addition. Fortunately, in the internet age, I could just capitalize these things, and that's shouting. So that means exponents do not distribute over subtraction as well. The way that you're going to remember this is you're going to look at this, but with plus. If I write 5 plus 3, 5 plus 3 squared, the parentheses say, do the addition first. 8 squared, 64. But if I look at 5 squared plus 3 squared, 5 squared is 25, 3 squared is 9. That's not 64. That's 34. Not the same. Now, it's all well and good when we're dealing with numbers, because everybody's like looking at this and saying, of course, we would not mix up the 64 and the 34. But if I trade that 5 and the 3 for an x and a y, all of a sudden we want x squared plus y squared. Take a look at what's missing from the 64 and the 34. And let's take a look at this 5 plus 3 squared. What this means is I need to take a 5 plus 3 and another 5 plus 3. If I take my exponent problem and write it as a multiplication problem, now I get to use the distributive property of multiplication over addition. And so I'm going to have a 25 plus a 3 times 5 is 15, plus 3 times 5 is another 15, plus a 3 times 3 is a 9. So here's the two 15s that are missing from the 5 squared plus 3 squared. You're missing a 5 times 3 and another 5 times 3. And that's the difference between the 64 and the 34. Exponents do not distribute over addition. Any questions? It's really important to make this observation, because if we trade our 5 plus 3 for an x plus y, we're going to want to distribute the exponent. But if we have an expression that says x plus y to the second, x plus y, these are not like terms, I can't add them. And I don't distribute the exponent to the sum, but I can write this as x plus y times another x plus, oops, I spelled plus wrong. And then if I multiply these with the distributive property, x squared plus an xy plus another xy plus a y squared. So I can't just x squared plus y squared, I'll be missing these two xy's in the middle. Just like with 5 plus 3 squared, I can't just 5 squared plus 3 squared, I'd be missing these two 5 times 3's in the middle. That's 30, and that's the difference between the 5 plus 3 squared, or sorry, the square of the sum of 5 and 3, and the sum of the square of 5 and the square of 3. Any questions? Can everybody picture what the next quiz is going to look like? It's going to have a bunch of exponents and multiplication all mixed up. And then sometimes you're going to be able to distribute the exponents, and sometimes you're not. That's going to be your next quiz, so take a look at that one over the weekend. And while you're doing that, I want you to think of the 3 things that we want to know about exponents. Think of the 3 things that we want to know about exponents. I made a page on it. Any questions, comments, or snide remarks? Great. All right, y'all have a nice weekend. Learn your 3 things about exponents. Keep an eye out for the quiz. It's supposed to show up today, but it's me that's running it, so who knows? Keep an eye out for quiz 1.4. That's going to involve operations with exponents, and then we're going to start introducing variables and stuff like we did down here, and see that this is all the same, MCU style. All right, that's going to do it for today. That's going to do it for this week. Everybody have a nice weekend, and thanks for playing.
You too. Thanks, Professor.